Hello, welcome to Agora, where we talk about the world through the lens of Christianity. I am your host Isaac, and today we are going to talk about Episode 8, Non-commutivity. In this episode, I want to talk about the self-imposed limits of the currently most widely acceptable scientific theories, and I want to relate that to man's finitude. In particularly, I want to talk about the limits of man's knowledge, and this is actually a self-imposed limit. In particular, I want to talk about the limits of observation, assuming that things really are what they are at the smallest scale as the latest physical theories have it, as the combined effects of objects and their interactions at the quantum level. You may have learned in physics that things have mass, a measure of resistance to movement caused by a force. They have speed, which is movement in a certain direction. They have momentum, which you could say is a kind of total moveness in the object. At the same time, things have a certain location or position in space, a relative location from a distance from any other thing, or some kind of absolutized position once you decide you want to stick to a certain reference frame. These are pretty common notions that we are used to in everyday life as well. Even if you do not like physics or don't know a lot of physics because you think there's so much math in it, and you don't like talking about terms like momentum or mass or velocity, when you're running or riding a bike or driving, you have a sort of intuitive understanding of it. When you're running, you know that it's harder for you to stop than if you were walking. You also know that it's harder for you to stop if you are running at the same speed, but with a backpack. You know there is a moveness in you. It's just whether you actually sat down and counted how much moveness you had. But you do know at a subconscious level that there is moveness. That's momentum. On the other hand, it's probably much more intuitive to understand position. Of course, when you measure the distance from yourself to the person next to you, you would usually measure, let's say, the distance between your closest foot to his closest foot. You two are facing each other. Do you measure from the sole of your foot to the sole of his foot? Or do you measure from the sole of your foot to the tip of his shoe? Or the tip of your shoe to the tip of his shoe? When we measure position in physics, we usually are interested in the moving center of motion that moves along with the whole body. Therefore, we use a kind of useful fiction called the center of mass. This is saying, pretend we very gruesomely crush you into an infinitely small spot, concentrating all your mass or heaviness there. You would mathematically be the same object if someone only cared about your movement behavior in space, when you are going to arrive somewhere, etc. Of course, you are not a dot, but a body with arms and legs and a head and muscle and bone and fat going everywhere. But that is not important. It is not visible to someone who is far away, who is wondering if you will crash into something else or how much damage you will cause if you crash into that something else. Now, if we don't think about it too much, classical mechanics, Newtonian mechanics, assumes momentum and position as things that can be measured at the same time. What that means is, suppose we advance technology and create the best telescope or camera we have ever invented. Then we can tell that something is exactly 30 steps away and at the same time moving at 40 steps a minute towards us. Wouldn't that be great? I mean, we already kind of do that in our daily lives, and we have to do that when we are driving. You have to judge both distance and speed of a certain vehicle that's driving beside you before you decide to turn and drive onto the main road. And there's nothing preventing us from doing it perfectly, right? Why can't we ideally do such a basic thing to utmost perfection? We tried doing that in the 20th century with an experiment called the double slit experiment, shooting the smallest thing we could at that time, the electrons, and found out that we could not measure their positions and momentum at the same time. Feynman talks about this in his lectures, Volume 3. If you cut two slits on a screen and shoot electrons through the screen, and you try to see which slit, which is the position, that the electron went through, then you will need at least a photon to bounce off of that electron. This is your camera. You catch the light that you sent out to record your image. Now the distance between the two slits, let's say, is 0.4 micrometers or 400 nanometers. If you shine a light with the wavelength of at least 400 nanometers, then we will get a fuzzy picture of the area around the two slits, and we can't say for sure which hole the electron went through. But if we shrunk the wavelength to get an accurate picture, we also jack up the energy of the photon so that the picture of the momentum, which is the location it ends up on the screen, is fuzzy. The electron might have landed either around the band or area of momentum P1 or the next band of momentum P2. If the momentum of the photon going upwards is slightly higher, it might end up into a farther band. If it's slightly lower, then it might have gone to the nearer band. You could easily tell how much momentum the electron had in the vertical direction. This is if the electron had no way to jump between the bands. But if the energy of the photon was big enough that the electron might have been bumped up or down to the neighboring band, then you can't say for sure which band the electron ended up at. This is the fuzzy momentum picture. Our detection method forces us to choose the door of knowledge number 1 or 2, either position or momentum, and locks the other doors shut once we choose a door. In quantum mechanics or in any physical theory that has received a quantum mechanical treatment and starts to view things as waves of some sort, for example, taking the Copenhagen interpretation and seeing those waves as probability amplitudes, the ultimate reality is divided into something behind the scenes, the unobservable but strongly inferred waves that are described either by wave functions, or if you don't want to assume beforehand that those things are waves, you represent them by mathematical objects called vectors. Behind the observable things such as position, velocity, energy, which are described either by operators on wave functions or matrices that transform a vector in a way that turns the vector into a multiple of the same vector. That vector would be called an eigenvector, and the constant that the vector is multiplied by is the eigenvalue. Now, if you assume that these things are waves, the Schrödinger way, then you have already assumed something about the universe and the things within it. You say that they are like water, like a continuous thing that is already everywhere, or might as well be everywhere, but will only show a bit of itself to you when you measure it, because you measure the concept or observable that you want, let's say position, and you force it to tell you that it is in one spot. But it's a wave, or a probability amplitude under the Copenhagen interpretation, and the wave is already everywhere. The same thing with momentum. The particle is this loving and all-embracing entity that is just everything and everywhere and wants to be everything to you, so it allows you to interact with it but never lets you control it. By its very wave-like nature, it can't be controlled the way you want to control it. This means that at the end, although you may have heard about how electrons and light and everything have particle-wave duality, at bottom, it really is a wave. The duality is fake, and uncertainty prevails. So then we take a step back and just do humble matrix mechanics the Heisenberg way, first formulated by Heisenberg in 1925. How about we don't assume that it's a wave, because that already assumes too much structure of the mysterious thing. Instead, we let it be that mysterious something, and we only talk about the math that describes it. Let's say that this something is called Jimmy, and for fun we pretend it's like a person. Jimmy is just there, jimmying about, whether being a particle or a wave or being some complicated entity. We don't want to assume about Jimmy. Well, maybe just a little bit. We assume Jimmy obeys basic math. We don't go looking into Jimmy's particleness, Jimmy's waveness, Jimmy's xness, but we say that Jimmy takes just as many roles as we can see. Jimmy has been A before, so we say that Jimmy has A-ness. Jimmy has been B before, so we say that Jimmy has B-ness, and so on. Jimmy can be a linear combination of A and B and C and so on, which is another assumption, but fairly harmless. Jimmy sometimes might even be anti-A-ness. Giving Jimmy this much freedom, we now start to ask Jimmy the questions we are interested in. Where are you, Jimmy? Let me know your location. But when you force particle or this whatever something Jimmy to tell you its position, Jimmy now has to pose and smile for your location locating camera one way that best suits the camera. We get information P for position. That gives you the ideal, perfect location of Jimmy with 0% error. But then you take out a different camera and ask Jimmy to tell you how fast it is moving. Show me some dance moves, Jimmy. How fast are you moving towards me? And how twisty is your head spin? Now Jimmy has to pose a different way that'll mess up the perfect position pose, but give you the best shot for determining its movement, its momentum. We get information M for movement. The fact that Jimmy's one move or state for the camera for information P could actually mess up the detection by the camera for information M is called non-commutivity. Mathematically, if you have P as the matrix operator for position and M as the matrix operator for momentum, and you multiplied it first M times P, and you subtract P times M from it, you will get a non-zero value. If we ask Jimmy to pose for camera P and then for M and stack the two pictures one on top of the other, and then pose for M and then for P, and then stack the two pictures one on top of the other, and compare the two synthesized pictures, they will look different. In fact, we have proved that they will always be different for these two kinds of information, P and M. An interesting question is that maybe we'll just have to invent a better camera. But the camera in our example is already assumed to be the best camera possible. There is something in mathematics called group theory, which tells us that if we believe Jimmy does behave like a linear superposition of states, this part is the thing we have to take on faith. That is representation theory, which tells us that we believe that particles do behave like these certain mathematical objects and are governed by these mathematical rules. Then it has nothing to do with the camera, but has everything to do with who or what Jimmy is. So we can never get perfect knowledge of Jimmy if we assume that Jimmy is what group theory assumes it to be. The faith or assumption that Jimmy is an object in group theory that can be faithfully and completely represented by matrix calculations is called representation theory. And if he can be represented by matrix calculations, then we modern people with computers would be elated because computers do matrix calculations very well. In both these formulations, we see that we are creating theories and assumptions of what basic reality is. And of course, we probably operate on a reductionism that says that all of reality, our first-person human experience, our human emotions, our thoughts, biochemical reactions, electricity, nuclear reactions, weak decay, all these can be reduced to ever more basic levels, and it seems like finally we are able to reduce physical reality to math, or at least matrix multiplication. For a more nuanced discussion of the limits of reductionism at a relatively popular level and a wonderful read, I would recommend Douglas Hofstadter's Gödel Escherbach. Basically, you can get reductionism at a cost, and that is correctness. Different categories at ever higher levels can form a coherent system, but their predictive scope is limited, and the validity of every prediction or concept outside of that scope is limited. But I think something interesting in these formulations is that they force us to theorize the world in a Kantian way. They both set out the limits of what we can observe and how we can observe and how precisely we can observe those things, while pointing out that there is a real something behind all that, although we can't ever observe it or even calculate it. Why would we want to or even come up in the first place with a theory that tells us that there are entities or sets of entities we can't even observe? The only reason is that they currently make the most accurate predictions of their effects. The natural world tells us that we will understand it best or make the most accurate predictions when we understand our limitations in making those predictions as well. The path to the most knowledge of the universe is a path that must admit at the outset that this knowledge is limited. If we want to have our cake and eat it too, then we have had a few thousand years, a few geniuses in computers to help us. But this is the best we can do. We are then forced into two options. Number one is that we say that we have gotten the theory wrong still, and say that we don't know if we can't ever know how the universe works. We aren't quite willing to accept confirmed non-omniscience, and would rather pretend that omniscience is still out there for us to grasp, even the omniscience that will allow us to say that there is no God. But the fact that we can't even do that means that we can't say that there is no God. That there is no God is a matter of faith, and an unreasonable one at that. Number two is that it can be said of the natural world that it works in ways that are controlled by some laws that undergird our current physical theories, which would then be understood as, per Gödel Escherbach, flowing in a higher level of abstraction. Maybe oscillators are the lowest level, or maybe it's built on yet another layer. But this layer itself already cuts us off theoretically from ever acquiring total information of anything. All the layers that can be reduced one by one to this layer are forever enclosed within the realm of limited validity. We might say as loudly as we want that there is no God in science or the confirmed theories of science, but science tells us that the confirmed theories of science don't tell us everything outside of science, and can itself prove to us that there is quite a large area outside of science but within the universe. We can call this a sort of distance or gap between us and total knowledge. There is something fundamentally incoherent in Richard Dawkins saying that there is no God and that the Navier-Stokes equation is notoriously difficult to solve. Why would the disproof of God be any easier than the Navier-Stokes equation? Furthermore, why would the disproof of God, whether factually in assuming God does exist, or contrafactually in assuming God doesn't exist, as being personal, sin-forgiving, accepting of animal sacrifices, be any easier? If you wanted to disprove God at all, the scientific method and science as it now obtains is a poor candidate. In the Bible, there are all kinds of senses of distance between God and man. There is this sort of metaphysical or epistemological distance where God is the creator and we are the creatures. There is a sort of ethical distance where God is the holiest personal being there is. Sometimes these senses are expressed spatially as God on the mountain of Zion. Of course, God is not confined to the location of the historical mountain that was called Zion outside of Jerusalem. Neither is God confined to the skies or outer space, but those concepts just help us understand that God is at some sort of distance, at some description. We might say at some distance of being, with the higher distances as being less accessible to us. God is at a higher spiritual level above the physical universe, like how the heaven is above the earth, like how the hill of Zion is above the plains. Likewise, we can say that God, being the creator, possesses a level of knowledge and control over the universe inaccessible to us. God's freedom and power and knowledge of the universe is total. Ours is not. This also has an application on one of the thorniest questions about God, the problem of evil or suffering. The Bible itself makes this application very explicit by using the book of Job. When Job doubted God's fairness and justice and wisdom concerning all the bad things that happened to his family and himself, God answered him from a very interesting place, the natural world. The distance of wisdom in the natural world was used as an indirect answer to the question of the problem of evil, at least at the moment of asking. God did not restore Job's fortunes yet, but used that exact point of doubt of God's justice and love to spring the question, do you have faith even at that very moment? An interesting point is that the Bible doesn't shy away from saying that the evil and suffering came from the hand of God. Job 42 verse 10 says, "And the Lord restored the fortunes of Job when he had prayed for his friends. And the Lord gave Job twice as much as he had before." Continuing on, verse 11, "Then came to him all his brothers and sisters and all who had known him before, and ate bread with him in his house. And they showed him sympathy and comforted him for all the evil that the Lord had brought upon him. And each of them gave him a piece of money and a ring of gold." What is emphasized is the restoration of Job's fortunes, which are not only material and physical, but also relational. And all of this was still while Job was on earth, in this stage of Job's eternal life. We should not only look at what Job asked before his restored fortunes, but also what he did not ask after the restored fortunes. And that is the very same problem of evil. We don't see a postscript of Job looking back and asking, "But what was all that previous suffering about? Why not just bring me to this chapter?" If we understand the sobering, weighty power and reality of suffering that challenges the possibility of goodness at all, that has consistently been the strongest driving force for doubt for the existence of God as embodying that goodness, then we should understand that the whole point of faith in God is to affirm that He is even able to overpower even this very challenge against God's goodness. His goodness is not only so good and vast that it has this almost intoxicating effect of making us forget Himself even, the giver of goodness, but to forget all the suffering that we just went through. And that is the promise of Job. This is a bit ironic since we care more about the suffering than God, therefore we forget God faster than our suffering. We think that suffering is a bigger concern than God is. But God wants to change us to be the opposite, to forget suffering faster than we forget God, to make God a bigger concern for us than suffering. And if you know God and come to accept that He can be greater than the suffering, then you affirm His infinite goodness in this test that really matters. When we just talk about it, we either underestimate the struggle with suffering or blow suffering out of proportion. And that really reflects how much we have pondered about suffering, but how little time we have spent pondering about God. Just as we might think about how big a leviathan is, how indestructible a hippo is, how incalculable and insimulatable the universe is, you probably chuckled slightly when I said hippo. Since we still would be able to hunt and kill a hippo if we really wanted to, maybe with a rocket launcher. But what about that mysterious creature called a leviathan? Maybe we are even more willing to accept that God could be wise enough to order the universe to operate in ways that our math cannot describe, more so than we are willing to accept that God could be wise enough to deal with the problem of suffering. But all these little stepping stones of faith should likewise help us in answering how pain and suffering comes to mankind, and especially to God's own Son, Jesus, who did no wrong. Our episode concludes here. If you have any questions or suggestions or things to correct about the podcast, please send me an email, and I'll see you next time. Bye-bye.
Yeah.